Go?
Go.
Woo! All right, period 7 fuss came on and ruined our lives. So we're just making a quick video. This is the theorem that we were proving just as the bell was ringing. This is something which is very obvious. It says that if the derivative is 0 on some kind of interval, then the function is constant. Again, the flow of information is from the knowledge about the derivative to knowledge about the function. Of course, if the function's rate of change is 0, then it just means that the function is not changing. So this is kind of obviously true, but a proof of this requires the mean value theorem. And so what we do is we suppose that we have a function whose derivative is 0, and we try to prove that the function is constant. We kind of did all this already. What does it mean to prove that a function is constant? It means that all the x values give the same y value. And so what we did is we took two arbitrary points, x1 and x2, and we tried to show that they have the same output. And why? Well, if you just apply the mean value theorem to this function on this interval x1, x2, then it's the mean value theorem which enables us to say that there's this special representative point, this point where the instantaneous velocity or the instantaneous rate of change at that moment equals the average rate of change. So for any interval whatsoever that you give me, say this interval x1, x2, I can always match what the function is doing on that interval to what the function is doing, so to speak, at one special moment. But what do we know? We know that the derivative is 0 everywhere. And so since the derivative is 0 everywhere, the derivative at this special moment is guaranteed to be 0 also. And as these two have been linked by the mean value theorem, it means that the average rate of change has to also be 0. And the only way for the average rate of change to be 0 is if there is no change. So specifically, since f prime of c is 0, then this whole fraction is 0, and the only way for this fraction to be 0 is for the numerator to be 0. And if the numerator is 0, it means indeed that there was no change. Okay, so this is kind of a silly theorem because it's sort of obvious, but this theorem is important because it can be used to prove this other little theorem. I call this a corollary. A corollary is a math word for little theorem that is kind of like 2 steps away from something you've already proved. Okay, and so take two functions that have the same derivative. Okay, in the other classes I said, I asked them, what does that mean if two functions have the same derivative? And people sort of spontaneously said, well, if two functions have the same derivative, then it means that they're changing at the exact same rate. And indeed, if the derivative is the same, then at any given moment, the slopes of the tangent lines are the same. So it seems that these functions are just vertical translations of each other. That's the common sense answer. The derivative is kind of like the coach telling you what to do, go faster, go slower, go faster, go slower. And if two different functions are following the exact same coach, then they must be doing the exact same thing, but perhaps at different in different positions. Okay, so this is sort of an important fact that we need to know, that indeed two functions with the same derivative are vertical translations of each other. And the way to prove this uses the theorem that we just talked about a second ago. If two functions, to show that, we suppose that these two functions have the same derivative, and then we make a new function. We do this trick again for the second time in this class, where we create a new function h, which is the difference of f and g. This solves our problem because the derivative of h is just f prime minus g prime, and by assumption, since these derivatives are equal, then the difference between them is 0. Well, now I have this function h whose derivative is 0. By the previous theorem from a second ago, this means that this function h is a constant function. And if h is just f minus g, but it's also a constant function, that proves that f is just g plus a constant. Okay, now the really, really important thing, which I saved to the last 10 minutes because that's what I always do, is a theorem about when a function is increasing and decreasing. And this requires that you have appropriate prerequisite sort of knowledge about what it means for a function to be decreasing. Okay, well, the common sense says that a decreasing function is a function which is just going down, but it has to be going down, everywhere. And so that we make this precise by saying for any 2 points whatsoever, a function is decreasing on an interval when, if you move right, the function goes down. Okay, so to be a little bit more precise, if to say that f is decreasing on an interval is to say that for any 2 points whatsoever on that interval, if you move right, if x2 is bigger than x1, then the function moves down. The value of f at x2 is less than the value of f at x1. Okay, so this definition has no calculus in it. It's like a pre-calculus definition of what it means for a function to be decreasing. Okay, well, now comes the central sort of theorem about the derivative, about when we know a function is increasing and decreasing? And the answer is something that is kind of obvious enough that you've probably known it already, which is that if the derivative is negative, the function is decreasing. And we've seen this already because even if you try to just draw a function whose derivative is negative, you know, if the tangent line has slope negative, it sort of feels like the function is decreasing, and that's just true. We have not mentioned this theorem out loud. Never mind me, just look at the board. We haven't mentioned this theorem out loud because proving this theorem requires the mean value theorem. And again, we have information about the function, which is being used to conclude information about the derivative, and we're going to conclude information about the function. So the mean value theorem is relevant. How do you prove this? The proof is just easy or really hard, depending on your experience. But basically, this is a conditional. This is an if-then statement. So we assume that the derivative is negative, and we try to prove that the function is decreasing. Okay, what does it mean for a function to be decreasing? Well, we have this definition right over here. A function's decreasing if, whenever you move right, the function goes down. So what we now do is we take any 2 points whatsoever, x1 and x2, and we try to prove that they have the move right, go down property. That is, when you move right, the function goes down. Okay, so then we'll suppose that these 2 points have the property that this is the bigger one. In other words, we've moved right, and now all we have to do is prove that the function goes down. Okay, well, from this information that x1 is less than x2, how do I prove that f of x1 is greater than f of x2? We just use the mean value theorem. So you apply the mean value theorem to this function on this interval. And the mean value theorem says that somewhere on this interval, there's this special representative point C. And this representative point C has the property that at this moment, the instantaneous rate of change equals the average rate of change. And this is the average rate of change. Okay, but we know something about f prime of C, which is it's negative. And so sort of the instantaneous rate of change being negative everywhere tells us that the average rate of change is going to be negative for any interval whatsoever. But okay, since f prime of C is negative, this fraction is negative, but as the denominator is positive, the numerator must be negative. And if the numerator is negative, it means that indeed f of x2 is the smaller one, as required. Okay, of course, it's also true, conversely, it's the exact same kind of logic, that if the derivative is positive, then the function's increasing. All right, so now what this means is that combined with these two theorems, we now have the ability to analyze a function and to know on what intervals it's increasing and on what intervals it's decreasing. Okay, so I crammed this into like the last 30 seconds of all the other classes. Take some kind of really simple function like this polynomial. This is the thing that we did not know how to do all throughout pre-calculus. Take the derivative. It turns out that this derivative is like a nice happy function which can be factored as a nice happy cubic. And since it's very easy for me, this is a sign chart for f prime, I now apply the theorem from a second ago. The derivative is negative on this interval, the derivative is positive on this interval, then the derivative is negative, and then the derivative is positive. And so immediately I can tell you that my function is decreasing on the interval from negative infinity to negative 1, increasing on the interval from negative 1 to 0, decreasing on the interval from 0 to 2, and increasing on the interval from 2 to infinity. Okay, so as long as you know how to differentiate a function, and as long as you know how to make a sign chart for that derivative, then you know exactly when a function's getting bigger and getting smaller. Okay, goodbye.